Hello and welcome to the supplemental handout on the center of mass and the moment of inertia. So here we're going to discuss how we can use calculus, specifically integral calculus, to find the center of mass and the moment of inertia of a continuous solid object. So this would be like finding the center of mass of a rod or finding the center of mass of a cone, okay? Which we're not going to do as an example, but as a general idea, all right? In fact, in this handout, I'm going to focus entirely on rods. I think they're easy to visualize. We can think of this as being, a long rod of constant width, right, constant diameter, and we can think that maybe it has totally uniform and therefore should have a balance point right in the middle, and we should be able to show that. Or we can think of rods that have non-constant density. They have non-uniform density. So the density maybe it's made out of aluminum over here and it's made out of lead over here, right? And it gradually changes. The density gets gradually denser as we move from one end to the other. Well, where would the center of mass be in that case? Where would the balance point be? If you wanted to balance on your finger, well, you'd want to put that closer to the denser end, right? So we should expect the balance point, in other words, the center of mass, to get moved to the side. And when we talk about the moment of inertia, we're going to do the same thing. We're going to consider the moment of inertia of a rod, and a rod that varies in density, that gets denser on one side. And I think this is going to be a good way to illustrate the basic idea of what we're talking about with center of mass and moment of inertia. Okay? Now, we'll talk about moment of inertia in a moment, but let's start with center of mass. So, here is the formula for the center of mass of continuous objects. This formula uses calculus in each case, and this is just in the three cases of x, y, and z. In this handout, we're only going to focus on x because we're only going to be dealing with rods, and rods are one-dimensional, okay? We only care about the x-axis. The y-axis has no bearing, and certainly there's no z-axis. And that's because of symmetry in x and y, right? Or rather, because in y and z, because it's just a circular rod, right? It's symmetric about those axes. Okay, so what does the formula tell us? Well, this is just the x center of mass, okay, the center of mass we care about. This is its location relative to some origin, such as in the figure below. Let's make it so we can see both simultaneously. So that'll be measured relative to the origin, x center of mass. This is dividing by 1 over the total mass of the rod, okay? And then what are we doing here? Well, we're integrating. Well, what is integration? Integration is an infinite number of small sums. So it's an infinite number of infinitesimally small sums. So we can think about this as comparing it to the center of mass for a discrete system, where we'd have 1 over the total mass, and then we'd take little individual masses. You imagine we had 16 little balls lined up in a row. Well, we'd want to know the coordinate of each of those 16 little balls, right? So we'd sum up each of them and so on, right? And we'd find their x-coordinate, and then we'd find the mass of each ball, right? And the mass of each ball could be the same or it could vary, right? Well, here, the idea is we now, instead of having 16, we're having 16 trillion, or so many that effectively each little summation is infinitesimally small. So instead of summing up on the discrete mass of each ball or particle, instead we have dm, a differential of mass. This is the mass element, a tiny piece of mass that then we can sum up an infinite number of. Of course, the integral itself represents that infinite sum. And then, because the formula takes into account the location of each of those mass elements, there's x. So this is like the x location of each mass element, all right? Now, does each mass element have to be the same? No, because we can have non-uniform density. So we can have the mass elements gradually vary in their effect on the center of mass, just vary in how much mass each mass element has, infinitesimally small or not. Now, here's the other thing. When you look at this integral, hopefully now, the justification of what all the variables, what they all mean makes sense. But we're still left with a problem, because we can't solve the integral as written. And we're going to see this in the example below. How do we actually approach this problem? How do we integrate over mass? Because, we have a variable x, and then we have dm. X is dependent on dm, but it's not obvious how we actually solve the integral. Okay? So let's see how we would do that. Let's read our example. A thin rod of mass m and length L, all right, and we don't need to define what they are because they're not going to affect the result. There's placeholders here. So some mass, it could be a kilogram, some length, it could be a meter. It doesn't matter. Has uniform linear density, okay? So this is the variable for linear density. It's the Greek letter lambda. And what linear density is it's kilograms per meter, okay? And compare that to normal density, which properly would be called volumetric density. And density, volumetric density, is represented by rho, and that's kilograms per meter cubed. Okay, that would be the units of it. Now there's also area density, which is sigma, and that's kilograms per, you guessed it, area squared. And it depends on the problem here. Now, of course, the rod, we're assuming, isn't infinitesimally thin on the y and z axes, right? It does have some diameter, but we don't care about it because it's not going to affect our balance point because, it's symmetric. So we only care about the density along the x-axis, which could be any axis. And since we are restraining our thinking, restraining our concern to a single axis, we only care about the density along a single axis. That's why we use linear density. And again, in this entire set of notes of thinking about, calculating centers of masses and moments of inertias, well, here's the thing: you only are going to use linear density because it's all going to be rods. Okay? Keep things simple. But the extension to area density and volumetric density isn't particularly difficult, but it is an extra step. Okay? So hopefully that makes sense. Linear density is just mass per length. Okay. All right. So this is here's the idea. And this is for the uniform rod. So the linear density is just m over L, right? Now, what does that mean, uniform? That means it doesn't change, right? So whatever the rod is made of on this end is also made of the same thing on the other end. So then question A is, where is the center of mass of this rod located along the x-axis? Well, if it's uniform linear density, then we should expect the center of mass to be right at the center. It should be at where? X equals L over 2. That should be our center of mass. Absolutely, right? Okay, so that means that this formula up here, the integral version of finding the center of mass of continuous objects, better work. It better give us x com equals L over 2. Let's see. Okay, so here's the idea. When we think about the linear density, we actually use that for something. Because what we're going to do is we're going to rewrite our mass element, our infinitesimally small piece of mass, as that linear density times the actual infinitesimally small length dx. That makes sense, doesn't it? I mean, check out the units, right? So dm has to have units of mass because it is, after all, a tiny little piece of mass. The linear density is kilo. Yeah, it is. Okay, excuse me. So mass, there we go. And then linear density is kilograms per meter. All right, and then we're multiplying by dx, which is the tiny small length, and that's meters. So then the meters cancel out, and then we are left with kilograms equals kilograms. Okay, so this makes sense to replace dm with lambda times dx. And this is the substitution we do every time, okay? Because that's going to allow us to actually solve the integral. Because now we're going to be integrating across x, right? Or integrating over x, and then we're going to have x inside the integral, okay? And in this case, our linear density is just a constant, isn't it? Look, because m is a constant, L is a constant, so that means the linear density itself is a constant. All right, so we'll write our integral definition of the center of mass, replacing dm with lambda dx. And when we do that, that's when I switch my limits of integration from being undefined to being definite, or indefinite to definite. And here I'm going from 0 to L. All right? And because that makes sense, because now it's clear that I'm integrating over x, and x goes all the way from 0 to L for the total rod. Okay? Here, I mean, I guess the limits would be 0 to m, but since we're never going to solve the integral, it doesn't make sense to put the limits in there. Okay, so this is the integral we're actually going to solve. All right, and for uniform density, as I said, lambda is a constant. And what do constants do in integrals? They come right out. We can just pull them right out because neither m nor L are functions of x. So they come right out of the integral. Okay, so here we are. You can see I've labeled it, but this is just lambda m over L. I pulled it out of the integral. That does allow us to cancel out m, okay? Because the center of mass should not be dependent on the mass. Okay, it only depends on the distribution of the mass. And here the distribution of the mass is uniform. Okay? All right, so then we're left to solve the integral itself. Not a very difficult one, right? So then we do our rules of antiderivatives for a polynomial. Our x becomes 1/2 x squared. Evaluate it from 0 to L. All right? And so then we can see, and this is probably the only time I'll do this, but the lower limit, the 0, we can see that when we subtract it, it's just 0, right? Because it's just 0 squared is 0, so there we go. All right, our upper limit just becomes 1/2, when evaluated, becomes 1/2 L squared. All right, we're almost done. Look what's going to happen. We're going to be able to cancel one of our L's, because we got an L here, and we got an L squared, which means that one cancels like so, and we're left with 1/2 L. the result we expected for a uniform density rod. The center of mass is right in the geometric center, exactly halfway down its length. Good, it works, okay? And we saw the important step that we're going to do every time, replacing dm with lambda dx, every time. And in fact, even when we do the moment of inertia in just a moment, okay? All right, so now let's do part B, question B. If instead the rod has a linear density that varies with length linearly, right? So, okay, so when I say linearly, that means it's going to gradually increase. And there's a lot of, use of the word linear here, but that means it's going to gradually increase. At one end, it's lambda naught, okay? Again, just a placeholder, and that's at the left side, all right, the origin. And then it's going to linearly increase, so steadily increase until at the far right side, at the end of the rod, where x equals L, right here, the density is going to be lambda equals 2 lambda naught. It's going to be twice as dense. So we have a rod that is gradually getting denser from some initial density to a density that's twice as dense at the far end. Okay? That is our non-uniform mass distribution, our non-uniform density. Okay? All right. And now we're going to find the center. Where should we expect the center to be? We should expect it to be closer to the end. So it should be something bigger than a half. All right? So it shouldn't be less than 1/2 L. It should be bigger than 1/2 L. Maybe 3/4, right? But probably not that dramatic. Okay? So let's see. Okay. So first we want to do something that's interesting and potentially tricky, but I think I'm going to explain it in a way that you'll see that it really isn't. We need to find the actual function of lambda based on the information we're given. Because we were just told 2 bits of information. We were told what lambda is at one end and what it is at the other end. Okay? So here's the result. Okay? This is the actual function of lambda. This is lambda as a function of x. Okay? Lambda naught is just that placeholder. It's the initial density at the origin. And think how this function works. If I plug in x equals 0, then this whole term over here goes to 0, and then I get that lambda just equals lambda naught. Well, that's exactly what it should be, because at the origin, the density is just lambda naught. If I plug in x equals L, then I would get L over here, which is 1, and then I'd have 1 plus 1, which is 2, so then I'd have that lambda equals 2 lambda naught at the far end, when x equals L. So this function definitely works, right? But is that the way to come up with it, just to kind of reason it out in your head? No. There's actually a tool, which we're all familiar with, which is the point-intercept method of finding the equation of a line. Honest to goodness, that's all we need to do here, because that's what it is, right? We're given the intercept, we're given a value at the origin, and then we're given one other value, the point, which is the value at x equals L, right? So look, I drew it out. I drew a graph of lambda as a function of x. I drew in the 2 bits of information we were given. We were given, at the origin it's equal to that the density lambda is equal to lambda naught, and at x equals L the density is equal to 2 lambda naught. So those are my 2 points, all right? The point and the intercept. Furthermore, I know it's linear, so then I know that I am looking for the equation of a line. The equation of a line is y equals mx plus b. M is just rise over run, so that's just going to be the vertical change, which is lambda, over the horizontal change, which is L, so there we can clearly see what M is. And then my intercept is lambda naught. Okay? And I found M by just finding comparing the 2 values. All right? And then when I clean this up a bit, I get the expression that I wrote over here. The functional dependence of lambda on x. This is lambda as a function of x. This is the linear density as a function of x. Okay. All right, so let's proceed, because now the process is going to be quite similar. We're going to start with the definition of the center of mass, right? It's the one up in the key formulas. Replace dm with lambda dx. But it's different now, because lambda is not just a constant. It doesn't just sit there, right? It doesn't just become m over L and get pulled out. Instead, lambda becomes this whole business, a function, all right? But this is still lambda dx, see? Right? It's still lambda dx. And x is still there because that was in there in the definition. That's the whole idea, is that the position affects the center of mass. Right? So this is some position times the mass element at that position. Okay? Total mass is just sitting outside the integral, because that is still a constant. Always will be. All right? And so then what I do, one thing I do is I say, lambda naught is a constant, and that's multiplied, so I can pull it right out of the integral. Right? So this just equals. Got squeezed in there for some reason. Right? But then we have lambda naught over m, so those are our constants. Everything else is left inside the integral, because we're going to have to deal with it with the rules of antiderivatives for polynomials. So let's do that. So my x, my x becomes 1/2 x squared. My x squared over L becomes x cubed over 3L, right? Because it goes up a power and then I divide by that higher power, so 3. And then I'm going to evaluate the limits, right? Don't worry about the lower limit because everything will zero out, okay? And so there we go. This is just evaluating the upper limit. So then this one becomes 1/2 L squared, okay? And then the second term becomes L cubed over 3L. And right away we can cancel out one of those and then becomes L squared over 3. And these, should always be like terms. They have to be, by the laws of physics, right? So, if they're always going to be L squareds. So if you did everything properly, you didn't make a mistake in your algebra, which can happen, and so it's a good chance to check your algebra. This is where you check and make sure that that whatever if this is L squared, this one is as well. Okay, and for center of mass, there will always be L squared. Every term will be. Okay. All right, and then we just gonna clean things up a bit more. All right, so then we got lambda naught over m 5, 6 L squared. All right, that was our last step up here, right? Because canceling out, but doesn't look right. Still got a lambda naught in it, okay, and an m. That's not right. It's just supposed to be, some number multiplied by L, right? And 5, 6 is too big, and after all, why is it L squared? We're not done, right? What went wrong? Because when we did the uniform density, once we got to this step, we found just some fraction times L. We were absolutely done, but we're not with the non-uniform density. Interesting. That's because every time you do a non-uniform density, you got one other step. You have to do a second integral. And the purpose of that second integral, and it's a simple integral, but bear with me. The purpose of that second integral is to find m in terms of lambda naught. That way you can substitute it back in, either way, either substitute lambda naught in terms of m or m in terms of lambda naught, but then that will eliminate your terms here. And also, you'll every time take care of the extra L in the process. So it'll take care of the squared. Okay? All right, so let's see how that works. Okay, so the other integral you set up, and we'll see this with the non-uniform density when we deal with the moment of inertia. The second integral, I call it the total mass integral, which is a very appropriate name. All right? So to eliminate lambda naught, we take the total mass integral. All it is just saying, well, total mass is just integrating all those mass elements. Okay? It has to be. And before, that would have just been m in the story. And for when it was uniform density. M was just m, okay? But now m, of course, is dependent on that function. It's dependent on the function, the linear density function of lambda, right? And so then we have to actually figure it out and substitute it back in, okay? So we'll do the same sort of steps. Notice the only difference here with this integral compared to the center of mass integral is just no x, right? So we'll replace dm with lambda dx. We'll replace the lambda with the function, lambda naught times 1 plus x over L, in parentheses. All right, and we know where that comes from. Okay, then we'll go ahead and solve the integral. Okay, so when we do it, we're going to, our 1 here, the lambda naught's going to come out. The 1 will just become x, because just a linear term will just become a first order term. X over L become x squared over 2L. Evaluate at the limits, 0 to L, because it's the total mass, so we're integrating the whole way. All right. And so then we'll clean some things up. Again, these better be like terms, L and L squared over 2L, so then it's just L over 2. And so then we get that the total mass is going to be lambda naught, that placeholder initial density. It could be anything. It could be 5 kilograms per meter, or it could be 50,000 kilograms per meter. It doesn't matter, right? Whatever the initial density is. And then we have the 3 halves, right, which just came out from adding 1 plus 1/2, and then L. Okay. And then what we're going to do is that we're going to substitute this, replace m with that. See? We'll say, all right. So then, and actually I do it the other way. We could easily do that, right? I could say, m is just lambda naught times 3 halves L. Literally just plug that in, replace m with that, which will cause the lambda naughts to cancel out, cause the L to cancel out. But instead I've defined the initial density instead. That way I'll substitute that in, okay? And we're going to substitute lambda naught into the x common expression, into that one right there. Okay, so that's what I've done here. So notice, right, I've just replaced lambda naught with 2/3 m over L. So that's that right there. Okay, and that's lambda naught. See, they're all the same. Okay, the 1 over L is still there. I just pulled it off to the side. That's this 1 over L, 1 over m, that is. All right, and then the 5, 6 L squared, that's right there. Okay, so m's cancel and one of the L's cancel. Now we finally have our answer, 5/9 L. Okay, so indeed, the center of mass is shifted more towards the dense side, Not that much. 5/9 is not that much bigger than 1/2, but it is definitely a shift. All right? Okay. So that's how we deal with confirming the center of mass for intuitive cases and dealing with cases where we have a non-constant density, and specifically one that increases linearly, so we can find our functional dependence using some rules from basic algebra. All right. Okay, so let's look at the homework problem. It's basically going to be the same sort of thing. The only difference is that your rod gets 4 times as dense, but it still increases linearly. It's all the same ideas. It just goes from lambda naught to 4 lambda naught instead of 2 lambda naught. It's the only difference. So that means you should get a value for the center of mass that's bigger than 5/9, right? Okay, so now second topic, the moment of inertia. A lot of carryovers here. It's very natural to group these two ideas together because they involve a lot of the same calculus approach, okay? So the moment of inertia is defined as this integral here. And this would be the moment of inertia for a continuous object, for a solid continuous object, right? Which is exactly what we were talking about for the center of mass, right? That's why we have to integrate rather than sum, right? Because this isn't a system of, particles or balls or something. This is a rod, or, could be anything, a disc, right? But in our case, it's going to be a rod again, right? Same picture, same problem. There's variations on it, okay? All right, so I is, of course, the moment of inertia, all right? So the traditional moment of inertia for something like a rod is, about its center is 1/12 ml squared, okay? Well, where do formulas like that come from? Because really, you're given them in a table of common moments of inertia. Well, they come from this integral, okay? And it does look a lot like the center of mass. Now it has r, right? R is playing the same role. It's really going to be x for us. And it's really the only difference between the moment of inertia and the center of mass is instead of it being x dm, it's x squared dm, or r squared, right? Whatever your variable is, okay? That's really the only difference. Okay, and it has to do with the idea of what the moment of inertia represents. It represents the distribution of mass, but not just where it's balanced, but the distribution of mass and its effect on rotation. Its effect on rotational motion, and how more inertia means harder to speed up, harder to slow down because of the sluggishness of matter, which is inertia. It's matter's resistance to change. Okay, and it turns out that the form of that is integrating x squared over mass elements dm, okay? Okay, now this right here is called the parallel axis theorem. And it says that the moment of inertia, I know it's a funny name, but the moment of inertia of some object is equal to the moment of inertia about its center of mass, so the center of mass doesn't come up, plus the total mass of that object multiplied by h squared, where h is the distance between your chosen pivot point and the center of mass, okay? So let's think about one. So if we look up in tables of moments of inertia, just pause the video and look them up if you don't believe me. But the moment of inertia of a rod about its center, and this would be a uniform density rod, is 1/12 ml squared. Okay. Now, if you look up the moment of inertia of a rod that you're rotating instead of about its center, but about one end. So imagine taking like a meter stick and rotating it about its midpoint at the 50 centimeter line, and then imagine holding it at the 0 centimeter line and rotating it. It's harder to rotate it when you hold it at the 0, so we should expect a bigger moment of inertia. And if we look, a rod about its end is 1/3 ml squared. Well, where does that 1/3 come from? Now, we'll kind of show where the 1/12 might come from using calculus, but where does the 1/3 come from? We don't need calculus, we just need this parallel axis theorem, okay? So let me show you how. So we would take the rod about its end, start with its moment of inertia about center, which we know to be 1/12 ml squared, then add m, and then what's the distance from the center to the end? Well, that's 1/2 L, so we'd have 1/2 L, and then we'd square it. Okay, so then we'd have 1/12 plus 1/2 squared, which is 1/12 plus 1/4. All right, so that would be 1/12 plus 1/4 in parentheses ml squared. Well, what's a 12th plus a 4th? It's a third. All right, a 12th plus a 4th is a third. That's where we're getting the moment of inertia about the end. All right, okay, cool. All right, so now let's look at, with the kind of the general idea out of the way, okay, let's look at how we actually use this process, how we calculate it. using calculus, right? Again, there's going to be a lot of parallels, a lot of similarities to what we just did with the center of mass. Okay, so we got a thin rod, mass m, length L, has a linear density that varies. I'm not going to do the uniform case. I just want to jump right to the second case. It's the same case. It varies from a density of lambda naught at one end to, you guessed it, 2 lambda naught at the other end. Okay, so it's the same darn function for linear density. All right. And then we asked in part A, I asked, what is the moment of inertia of this rod about an axis that passes through its left end? Left end would be the origin, right? So that's imagining it rotating here. So there's some pivot point, and you're rotating the rod, and this is giving its rotational inertia, saying how hard is it to rotate about that end? Okay, great. And we know 1/3 is when it's uniform. So what should we expect? Well, it should be bigger than 1/3 because since it's got more mass over here, that actually makes it harder to rotate. Because remember, the bigger moments of inertia are when more mass is distributed further away from the axis. A hoop has a bigger moment of inertia of a disk because it's got all its mass all the way away from its axis of rotation. Okay? All right. And then part B, we just move the axis of rotation, the pivot point, so to speak. We just move it to different things, and then part C, we move it again, and we're going to use the parallel axis theorem in part B and C. No calculus in those parts. The only calculus is going to be in part A. All right, let's do it. Okay, this is just kind of the idea of where we're going to find the different values in the different parts of the problem. So we'll get back to that in parts B and C. Okay, so here's the definition. The moment of inertia about the end will be, okay, just our general definition of, our calculus definition of the moment of inertia, and then we're going to think about how we're going to set it up, our limits here. So first thing I'm going to do is just replace dm with lambda dx, okay, absolutely. And then I'm going to carefully think about my limits of integration, because you do have to be a bit more careful. Because if you're rotating, then you have to make sure that you're integrating from the pivot to your final point. All right? And that's why I like to start with finding the moment of inertia about the origin, so that one of my limits can be 0. So, because I could set up this integral and I could find the moment of inertia about the middle, but in that case, my lower limit would be, I would go from negative L over 2 to L over 2. So I'd have different limits of integration, okay? And that would give me a different answer, okay? So the limits of integration mean that they're about the pivot, okay? Or in other words, I guess the way to say it is that 0 has to be at the pivot, because the idea is that there is no rotational mass if there's any mass located at the pivot. And so if I make the pivot the middle, if I make this the axis of rotation, the middle, then the 0 is at the middle, and that's why this would be negative L over 2, and this would be positive L over 2, because I've moved my y-axis to the middle, right, to the center of the rod, the geometric center. So your y-axis must fall on the pivot, and that's why here we're finding the moment of inertia about the end, because I'm calling the y-axis the end. So there's a real choice there. It matters, okay? So again, I think it's always good to find the moment of inertia with the intuitive case, with the end being 0, and then just use the parallel axis theorem to move it around. Okay? But you don't have to. You could do parts B and C with calculus and confirm that it works by actually just changing your limits of integration. All right? Okay. So then, find the moment of inertia about the end, 0 to L. Okay? X squared is just there, right? That was in the definition after all, right? Okay? And then we're going to replace lambda with its functional form, because lambda is a function of x. There it is. Lambda naught times 1 plus x over L, in parentheses. All right, we know that comes from the point intercept formula of a line. All right, our dx is there because we already did our substitution, replacing dm with lambda dx. All right, now we just solve the integral. Excellent. All right, everything's a higher order here because of the x squared instead of x. So 1/3 x cubed over here, and then 1/4 x to the 4th over L, right? Because when we distributed x squared, this became x cubed. So then when we integrate, it becomes x to the 4th over 4. All right, then evaluate our limits of integration. Lower one doesn't do anything. All right, cancel out one of the L's. So then we have a lambda naught 1/3 L cubed plus 1/4 L cubed, right? Because this is 3. Okay, all right, so there it is. So then we add 1/3 and 1/4. 1/3 plus 1/4 is 7/12. And so then we got lambda naught times 7/12 L cubed. Are we done? No, absolutely not. Now, because moment of inertias aren't just a fraction of L, so we shouldn't just expect some fraction times L, but their form is always going to be some fraction called alpha times the total mass times L squared. And we're not done yet because first of all, the total mass isn't even here, right? And it should be in the moment of inertia, unlike in the center of mass. M should actually show up, and it's L cubed, not L squared. So, and we're stuck with the lambda naught, so we're clearly not done. What do we got to do? Say it. We have to do the total mass integral, because that will then allow us to get our moment of inertia in the correct form. Okay? All right, so we need to find lambda naught in terms of m and L from the total mass integral. So we know from the previous example that lambda naught is just 2/3 m over L, right? So what I'm saying, I'm literally just giving us the results from the total mass integral we did before, because it's the same integral, right? It doesn't matter that we're finding the moment of inertia this time instead of the center of mass. The total mass integral is unchanged. So this is literally the result from the total mass integral, okay? All right, which I'm not bothering to do because we already did it in the previous example. Refer back to, the example from part 1. All right, so then I'm going to substitute this in for lambda. All right, and so here it is substituted in. There's a 2/3 m over L, which replaces lambda naught. That is not lambda naught. All right, and then we got our 7/12. We cancel out one of our L's, which is good, so we'll have the correct order. And then we're going to have an m, which we want. And we clean things up. There it is, 7/18 mL squared. That's the moment of inertia of a rod rotated about its end if that rod gets twice as dense gradually along its length. Okay? And is that bigger than 1/3? Yes, it is. It's just a little bit bigger than 1/3. Okay? Because 1/3 was for a uniform density rod. But here we have more mass at the end, so we should get a bigger moment of inertia. It's harder to rotate a rod that gets slightly denser at one end if you're holding it at the less dense end. Okay? Now, you could move the y-axis over here and find out how that it should be a little less than 1/3 if you're rotating it about the denser end. Okay? If you put the axis of rotation at the denser end. That would be fun, right? I didn't ask for it. Okay. All right. Now let's do parts B and C. We're just going to move our axis of rotation. So the first thing we're going to do is remove the axis of rotation to the center of mass. Here it is in decimal form, by the way. I think it's better in fraction form. All right. So then if we have the moment of inertia about the end, and then we got the moment of inertia about the center, and then we have the distance from the end to the center of mass is the location of the center of mass, right? But you would have to find that, okay? So if you were solving this problem for an unknown moment of inertia for a mass distribution that you hadn't just done in the previous example and found the center of mass for, found that x com was 5/9 L, then you'd have to find this. You'd actually have to do a third integral to move the moment of inertia using the parallel axis theorem to where you want it, or just do another just do another integral with different limits. But even if you do the different limits, you need to know where to put your 0 points. So you would need to know that the center of mass is at 5/9. So you actually definitely need to know that the center of mass is at 5/9 L. All right? Okay? And so then what I'm going to do is I'm going to solve for the center of mass, which means I have to move this one over here and subtract that one. So rearranging things, I get that the moment of inertia about the center of mass is the moment of inertia about the end minus m times x com squared. Okay? And by the way, that's because the parallel axis theorem always has to be in this form. It's always compared to the moment of inertia about the center of mass. You can't compare two moments of inertia around two arbitrary axes if one of those is not the center of mass. That will not work. That will give you the wrong answer. You always have to compare to the center of mass, and then if you want to then compare between two axes that aren't the center of mass, you have to take an intermediate step of comparing one to the center of mass axis, and then compare the moment of inertia about the center of mass to that new axis. Okay? And that's kind of what we do in part C, because part C then we move to the geometric center, right? Which is neither the end nor the center of mass. The geometric center is at L over 2. And in that case, we couldn't have, say, gone straight from A to C because neither of those would have been the moment of inertia about the center of mass. Okay? Okay. So then here we're going to do, we're just going to plug in our values. All right, so x com we know to be 5/9 L. Again, we know that, but you may have to solve it for a different problem. Okay? We know that our moment of inertia of our non-uniform density rod about the end is 7/18 mL squared. Okay, and then we're just going to do some algebra to clean this up. All right, so when we take, because these are like terms, by the way, ml squared and ml squared, and so I'm just taking 7/18 minus 5/9 squared. So in other words, I'm taking 7/18 minus 25 over 81. All right, when I put that in and I clean up my fraction, it becomes 13 over 162. Not the nicest fraction in the world, not as nice as 7/18, right? And so as decimal form, it looks like this. All right, we can see that it's significantly smaller, as it should be. Right, because rotating about the center of mass is a lot easier than rotating about one end. Okay? All right. There we have it. Big ugly number, right? And very different than 1/12. Okay? Now it should compare, kind of nicely to 1/12. Okay? So that's, but it's got, but it's definitely a different number. It is actually harder to rotate it because 13 over 162 is larger than 1/12. Okay? All right. Now let's do it about its geometric center, because this is interesting, right? This is because before this was like rotating it about this line here, 5/9, which is just a little bit bigger than 1/2. But what if I rotate exactly around its geometric center? Let's see what we find. All right, so here we're just going to do the moment of inertia about the center of mass that we know to be 13 over 162. And then we're going to find the difference between the center of mass and the geometric center, which isn't very much. It's just 5/9 minus 1/2. It's just this small gap here. Okay? All right, so that's our h. That's just moving our axis of rotation. Okay? And then it's just ml squared, so then these are going to be like terms. So because we have over here, oh, I dropped the square there, but there should be a squared. Just forgot to write it. All right? And so then when we plug in the numbers, 13 over 162 plus 1 over 18 squared, whatever 18 squared is, what do we get? 1/12. Whoa. The exact same as when the density was uniform. About the same point. Wait, is that right? It is, because of the linear effect. Now this, for the uniform density, this would have been both the geometric center and the center of mass. And we can clearly see that the moment of inertia about the center of mass for our non-uniform rod here is different than the moment of inertia about the center of mass for the uniform density rod. But what is the same is if we consider the moment of inertia about both of their centers, the geometric centers, they're both 1/12. And that's because it got denser. It went from lambda to 2 lambda, but it did it gradually. And since it did it gradually, when we consider the moment of inertia about that center, the effects exactly cancel out. And it's as if the density didn't matter at all. It didn't change, which is so cool. So you can show for any linearly changing density that about its geometric center, not its center of mass, it will always be 1/12. Okay? Which is a great way to check your work. All right, so that's it. Again, not a lot of new calculus ideas, just putting into practice differential substitutions and some integration of polynomials. Okay? All right. Well, thank you so much for watching. I hope it's been interesting and informative.